It's a pleasure to be here. Okay, so I don't know if, is there anyone here working on the Galactic Center? Okay.
Tough crowd.
What's that?
Tough crowd.
Tough crowd or easy crowd? Depends how you look at it. So I'll tell you a few things about what happens in centers of galaxies. And I will present some mathematical model that describes part of the processes that are happening. Some of the processes I will skip, at least at this stage. And it will give you some easy way to imagine what is going on. This will be the end product of this mathematical dealing. It's the left-hand side here. There are great observations of the Galactic Center now, especially with new instruments that the MPE group in Garching is doing. So they're getting tremendous resolution, and they managed to follow stars in, well, we'll get to that in a second. So, but there's a great observational progress on this. In other galaxies, it's a little bit harder to do, but maybe if LISA comes up sometime, we will be able to detect gravitational waves from star orbiting the supermassive black hole in the center of other galaxies. So this is a movie that gives you a perspective of from where we are, zooming in towards the galactic center, which is probably the densest stellar population, definitely in our galaxy. You know, around here, the stellar population is about less than 1 star per cubic parsec. And there, it's millions or even billions of stars per cubic parsec at the very center. At some stage, this movie shifts to the infrared because the absorption towards the galactic, the extinction, is huge in optical to the galactic center. So all the observations of the galactic center are in the infrared. And people have been observing this in different quality for the past 20 years or a little bit more. So they have been able to follow the orbits of stars. These are real orbits of stars in the galactic center, and calculate from that the mass of the black hole. Actually, the mass of the black hole, this is now a cleanup movie of the same thing that you saw, that before you saw the raw observation. And then you can do fitting of Newtonian orbits to this, and these are these blue lines. And part of that fit, you get the mass of the supermassive black hole, and actually also the distance to the galactic center. It's measured this way. When you think about it, if you just see an orbit on the sky, let's say you saw one of these orbits, and you measure the period and the size on the sky of the orbit, it doesn't tell you the mass of the black hole. Because if you don't know the distance, you don't know if it's a small orbit nearby or a far orbit away. So you don't have the physical size. So in order to complement that, you need at least 1 point of radial velocity. That actually gives you a physical measurement in meters per second. And then that dissolves that degeneracy between the distance and the mass of the black hole. But it basically gives you both the distance and the mass of the supermassive black hole. This is the same measurements from a competing group, the UCLA group. About the same quality of measurements. I think now the MPE group is slightly better because of this new instrument that they put in. This is the new instrument called gravity. So the mass, best measurement of the mass is 4 million solar masses. And it's about 27 light years away, or 8.2 kiloparsecs. The Schwarzschild radius of a black hole of that mass is about 0.1 AU. And this is the orbit of one of the most famous stars in the galactic center, called SO2. It's the brightest star that is very nearby to the supermassive black hole. There is one star which has even a smaller orbit, but it's too dim, so it's hard to follow. So this one has a pretty eccentric orbit. It has a semi-major axis of 1,000 AU, and yet it goes around the black hole within 15 years. And the periapse, this is the thing that enabled to measure that mass. And the periapse distance, the closest distance in here, is about 100 AU. And some people, when I show this slide, they think that something is wrong because the black hole is not in the center of this event, or not even on the main axis of the ellipse, but this is just a projection effect. You can convince yourself that if you take an ellipse, and the black hole is, of course, at the focus of the ellipse, if you project it, you can put the black hole anywhere you want in the projected ellipse. It doesn't have to be on the main or the minor axis. It could be anywhere inside, and it's reasonable. So this is where the black hole really is. Another parameter that will be important is the tidal radius, how close a star can be to the supermassive black hole before the star itself is destroyed by tides from the black hole. And this turns up to be 1 AU. So it's bigger than this. So you can go around the black hole without falling into the event horizon and get destroyed. But it's still much shorter than the current periapse distance of this star. So this star is pretty safe. It's not going to be destroyed. And at the distance that it is, even at the closest point, the tides are minimal.
What's that radiometric?
Say that again? OK. So what can we do in the future with this, or what they want to do in the future with this? So they already measured this. This is a Newtonian thing. They have the mass of the black hole and the distance to the galactic center. What they want to do, this they already did, is measure the gravitational redshift, the fact that when photons are coming from here, they are redshifted when they come to us. So this is the redshift due to the gravity of the supermassive black hole. So this is a GR effect, if you want. That's the lowest order GR effect that affects this. So for example, this is the velocity as a function of time, the radial velocity of this star as a function of time. And this is affected by GR, by the fact that when photons are emitted here, they are a little bit redshifted. So that twists this velocity curve a little bit, and it was measured. Within a year, maybe less now, they will see the Schwarzschild precession of this. So we know the answer already. If GR is right, we know the answer. We know they can measure it, and it will come pretty soon. If they won't measure it or they measure something different, this will be a surprise. What they can't do still, and I'm not sure even with this sophisticated instrument, if that's the only star they have, is to measure the lens Thirring precession. So the fact that space-time is drifting with a spinning black hole, that causes extra precession for the orbit above the Schwarzschild precession. If you measure that, that will teach you something about the spin of the black hole, and therefore something about how that black hole grew in time, and so on. But this is in the future. That's possible.
Are there any constraints on whether the black hole is a binary?
Yeah, there are constraints. I think I don't have that figure, but it depends on where you want to put the companion. That will tell you what must be the mass ratio. But roughly above 1 to 1,000 is excluded in most distances. So this black hole is not a major binary. Okay, it could have some flimsy, and of course it can have another solar mass black hole, and we won't know. But another supermassive black hole like this one doesn't exist.
So the lens Thirring effect is another smaller by precession by another factor of the ratio between the Schultz radius and the periapse distance. Right?
Yes.
And this is like a few orders of magnitude. So doesn't the idea that if you need 1 year to measure the precession, you need like thousands of years to measure the.
Yeah, that's what I'm saying. With this instrument and with this star, they're not going to make it. What they're hoping is that this instrument will lead to a high enough resolution that they now suddenly see new stars that they haven't seen before. Because these are the pictures, what limits them is confusion with other stars. If the resolution is better, the confusion is less, and all of a sudden they can see deeper and see dimmer stars there. And hopefully there is one star that is dimmer than that, but it's orbiting here. So with this star, all the precession effects are stronger, and the time scale to see them is shorter, so you'll be able to see it, hopefully. So if there are more stars like that, and part of what I'm going to tell you about the talk is to try to predict what is the distribution of stars around supermassive black hole, what sets it up, what it should be. Okay, so what kind of phenomena are happening in galactic centers like that? Our galactic center, but all of them. So, well, you can think of a star going very, very close to the supermassive black hole. And it gets tidally deformed if it's close enough, and eventually it starts spilling mass towards the black hole. It overfills its Roche lobe and starts spill mass. This is the same tidal radius that I described in here. So basically, if you have a star within 1 AU, solar mass star within 1 AU from the supermassive black hole, it will start transferring mass to the black hole. So I will try to estimate what is the rate of such events. Do we expect that there is a solar mass star now in the galactic center, transferring mass to the supermassive black hole? We couldn't see it. solar mass star is too dim. This SO2 that we discussed before is maybe 10 solar masses, so much brighter. Do we expect? How many? I'll try to answer that. I think the probability is maybe 10% that there is right now a star with 1 solar mass orbiting so close to the supermassive black hole. It will emit gravitational waves. This we would be able to detect with LISA if such a star exists there, so we will know. And another thing I'll try to tell you is that when a star in such a configuration overfills its Roche lobe, it spills mass not only towards the black hole, but also towards the other side. If you remember those Lagrange points, so the usual story is that you spill mass through the L1 point, but I'll tell you that in some circumstances you can also spill mass through the L2 point. So this is one thing. Another thing is tidal disruption events, which are basically explosions of stars by tides from the supermassive black hole. The distance for this to happen is the same 1 AU that we discussed, but it's a star that comes on a very eccentric orbit. It's not a star that is orbiting on circular orbit around the black hole. It comes from a very eccentric orbit, and in a sudden way comes too close to the black hole, gets destroyed, and never recovers. And then you have the debris of that star splashed around the center of the galaxy. These are the explosions that we think we see in other galaxies. I don't know, people are working on TDEs here? Some, okay. So tidal disruption events, we'll try to figure out the rate of those and how they compare with the more gentle events of circular orbits and destruction on circular orbits. You can have another destructive process, which is not on a single star, but on a binary. So there are 2 stars, they orbit around each other, then they come close enough to the supermassive black hole. Because they are slightly more separated than the size of each star, they are more easily destroyed. Same masses, but larger separation, so they're less bound. So they have a tidal radius which is a few AU. But if they come that close to the supermassive black hole breaks apart the binary. The stars can still survive. And the story is that one star is ejected away from the galaxy as a hypervelocity star. Do people know here about hypervelocity star? Anyone working on hypervelocity stars? Yeah, these are stars flying away from the galaxy at velocity, let's say, of 1,000 kilometers per second. They're unbound to the galaxy. There are very few ways in which you can produce a star that is moving at 1,000 kilometers per second. So that's a leading mechanism. And the other member of the binary lost energy. So you should think of a binary that came, its center of mass of that binary was on a parabolic orbit around that supermassive black hole, so 0 energy. One star got some energy, this 1,000 kilometers per second, and the other one lost some energy, so it's on some bound orbit around the supermassive black hole. And maybe this is the origin of some of the stars that we see around the supermassive black hole now. So all this is going to be part of the story. No, I'm not going to prove. It's a suggestion. We'll try to see what makes sense, what is the rate of that, and is that supposed to be an important mechanism. It depends on the fraction of binary in the galactic center. If the fraction is high, order unity, it should be an important thing. This is what I'm going to claim. Okay, so let's talk a little bit about mass transfer. I'm reminding you some basic stuff. Massive object, less massive object. These are the 2 Roche lobes. These are the regions where you feel mostly the gravity of one of the bodies. So if you're inside this lobe, you will orbit this mass. If you're well inside this lobe, you will orbit this mass. At this point, you sort of can't choose if you're orbiting this one or that one. And outside of those, you're orbiting the 2 as a single mass. This is roughly the situation. For extreme mass ratio, like what we're talking about, supermassive black hole and a solar mass star, then the size of this compared to the separation between the massive and less massive object is the mass ratio to the 1/3 power. Okay? This is where the tides are equal to the, if you're not familiar with this, can you see if I write here, or is it the binding forces to the less massive object is Gm over some distance little r square. This is the force. And the tidal force for the supermassive black hole, this is the force from the supermassive black hole, but the tidal force is smaller than that one by r over a. So when you solve that, the G cancels out, and you get that r over a cubed is m over m to the 1/3.
Well,
Yes. Okay. So this is small, this is big. And when this lobe is equal in size to the size of the star itself, then the star starts spilling mass towards the supermassive black hole. And what is famous from Lagrange time is that in this rotating system of this binary, you have several points, 5 Lagrange points, which are stationary. You can put a particle there, and it will stay there orbiting with the binary forever. Those 2 are stable points, and those 3 are unstable points. So here you're sort of being pulled to this one and to this one. And with the centrifugal forces, you're in balance here. If you're slightly inward, you will fall here. If you're slightly outward, you will orbit this one. And you see that the potential at the L2 point is slightly higher than the L1 point. That's why when a star overfills its Roche lobe, it will start spilling mass first through the L1 point. But I'll show you that in some cases also in almost equal amount from the L2 point. This is a situation here from X-ray binaries. It's a picture I took from the web somewhere. And then I changed it to be suitable for a supermassive black hole. It's really easy in PowerPoint or Keynote or whatever. I just took this one, I made this larger, and I took this one and made it smaller. And I stitched the 2. So I got something like this. So this is a star spilling mass through the L1 point towards the supermassive black hole, and then spirals in. Okay. So why would the star be here? Suppose the star was a little bit farther away, so the Roche lobe is bigger, but the star is still the same size, so it doesn't fill the Roche lobe, it doesn't spill mass. It goes around the supermassive black hole, and it emits gravitational waves. As it does that, it loses energy, it gets closer and closer to the black hole. Eventually, it starts spilling mass towards the black hole. And my question is, how will this system evolve? So we know that systems that emit gravitational waves, they get closer to each other. However, once it starts transferring mass to the supermassive black hole, the situation is unclear. Why? Because that mass that is falling here has to lose angular momentum as it falls towards the black hole within that accretion disk. And that angular momentum, through gravity, may find its way back to the secondary. So the secondary, if overall it gains angular momentum, may actually go outward. So gravitational waves by themselves, they cause loss of angular momentum from the system, and they will cause the orbit of this guy to shrink. And therefore, the frequency to go up, like the chirp we know from LIGO. This should be familiar to everybody. But once there is mass transfer, it can go either way, because that mass that is falling in here is losing angular momentum, and then that angular momentum may find its way back to the donor. And if that happens, it can go away. So this is probably what these 2 lines are trying to say. So gravitational waves cause the orbit to shrink, and the mass transfer may cause the orbit to expand. And in many cases, we have what we call stable mass transfer, in which those 2 things balance each other just such that you have a gentle mass transfer. So if we go back to the previous slide, you think about it this way. Suppose that this star fell too close to the supermassive black hole, so it now fills its Roche lobe very vigorously. It doesn't emit much more gravitational waves because it's only slightly closer to the supermassive black hole, but it overfills its Roche lobe, and there is too much mass transfer, so it goes away. As it goes away, there is less mass transfer, and that sort of stabilizes the system. If it's a little bit too far, so the spilling of mass towards the supermassive black hole is too slow, then only gravitational waves matter, and it comes back in, filling its Roche lobe even more, and until that nice sweet spot is being found. Okay, so when you understand that, you understand that the way that the system will evolve depends on how the size of the star depends on its mass. So when the star is losing mass towards the black hole, you want to know what happens to its radius. And there are 2 things that can happen. One is it can change to a new star, a new main sequence star with the new mass. Okay, so you can take the main sequence. You know the mass-radius relation on the main sequence, roughly linear. And you say, okay, as the star is losing mass, its radius is shrinking. And in that case, if it still has to just barely fill its Roche lobe, because its radius is smaller, it has to be closer to the supermassive black hole. So in this case, if that is the situation, you will have stars that are getting closer and closer to the black hole as they are still barely filling the Roche lobe. You can think of another thing. You can think, oh, the star, as it's losing mass, is just changing adiabatically. So you take hydrostatic equilibrium, gm squared over r to the 4 is roughly the pressure or energy per unit volume in the star, therefore the pressure. And the pressure changes as the density to the 5/3, adiabatic evolution of the star. If there is not enough time for conduction or convection or whatever is happening in that star to redistribute the energy. And then you can take those two sides and you get that the radius is going like the m to the minus 1/3. So that tells you if you do something very quickly on a star, you take some mass out of a star quickly. You don't let it become a new main sequence star. You just let it react to a new hydrostatic equilibrium without losing energy. So that's on a dynamical timescale of a few hours. It will go like the radius goes like the mass to the minus 1/3. You take mass out, the star swells on this timescale. Then if you wait a million years, which is the time that photons can diffuse inside the main sequence star, a solar mass main sequence star, then it will behave like a new main sequence star, and that power will become positive. So whether stars grow or shrink as they lose mass depends on the time scale in which they lose mass. So that leads to this understanding of what's going on for a main sequence star around a supermassive black hole. So you start with a very massive object, and you can calculate what's its time to distribute energy within the star, what is the conduction time or the photon leakage time from that. And it's relatively short compared to the gravitational wave timescale. So these stars, as they give mass to the supermassive black hole, they get closer and closer to the supermassive black hole because they shrink when they give mass. On the other hand, if you have a low mass star, it has to get very close to the supermassive black hole in order to fill its Roche lobe. The gravitational waves there are too strong. The evolution time scale is less than 1 million years, and the star evolves adiabatically. As it loses mass, it becomes bigger, and therefore to just barely fill its Roche lobe, it has to recede away from the black hole. So the gravitational wave signal that you will detect, instead of having an increasing frequency as a function of time, will have a decreasing frequency as a function of time. So instead of a chirp, it will be the reverse of that, which I call a preach. So those are chirping, and those are preaching, and you can have some even more complicated evolution along the way. So, so basically, I think when LISA is up, we can expect to see signals of stars orbiting supermassive black holes, if they are there, where the frequency as a function of time is going down rather than going up. Yeah, this is when LISA comes up. Okay, let me come back to this point. So this is a nice 3D print that someone did and put on the web of the potential in that rotating system. That you can see, this is the primary is in here with a very deep potential wave around it. The secondary is here with also deep, infinitely deep, because next to a point mass you have infinitely deep potential, but it's narrower because of the smaller mass. And this yellow material is sort of signifying that this object is filling its Roche lobe. And as it goes up, you see that it starts leaking through the L1 point. So think now that you're pouring some, what is this? It's not milk, maybe honey or something orangey in here. And it will spill back towards here. But what if you pour the thing too quickly? Then it will start overflowing the L1 more considerably in order to allow that rate of mass flow. And then it will start also spill from here. Okay? So if you have a system in which the bodies evolve due to gravitational waves or whatever makes that system evolve, and that evolution is too quick, you will have mass spilling out through the L2 point and not only through the L1. So for slow processes, only L1. For very fast processes, equally through L1 and L2. And you can calculate the rate and the mass ratios and so on, and you will see that actually for solar mass stars around the supermassive black hole in our galactic center, you will expect mass loss through the L2 point as well as through the L1 point. So stars that are losing mass to the supermassive black hole, about half their mass they will give to the black hole, and half the mass they will shove to the other side.
So the displacement at L2 from the surface of the secondary is q to the 1/3 times the radius of the secondary.
This thing is the difference in potential between the L1 and the L2 point.
Right.
So now you can calculate, given the time scale in which the system evolves, how much the fluid here. So here's a picture that explains this a little bit better. So this is now a 2D cross-section in the rotation plane. And this is the Roche lobe. And the star has to overfill its Roche lobe. So this is the gray area is the star. So the star is above the Roche lobe. And all that stuff is going out.
So you're saying outside the Roche lobe is leaving in an ample time. And then you have
Yeah.
a certain
Density here times the speed of sound here will give you the rate that the mass is flowing here. And I have to match that to the evolution timescale of the system. And then I know that distance, how much the star is above the Roche lobe. And if that overcomes the L2 point, then I'll have mass spilling through the other side. So this is a published work with, do I have his name somewhere? With Itai Lineal, my student.
For such a large mass ratio, the potential difference is very small.
Very small, yes.
And the molecule is measured
Yeah, so this is it.
just distance.
Yeah, this is measured in distance here. But it doesn't matter. It's the potential difference is also proportional to q to the 1/3. Yeah. So this is why this thing spillage through L2 is more likely in high mass ratio systems. On the other hand, high mass ratio systems, the evolution of the system is too slow. So that's against you. Right? You want a fast evolution, because if the evolution is too slow, then it's enough that the star is overfilling its Roche lobe by a tiny bit, and that gives enough mass to balance the... Yes, the gravitational wave for high mass ratio, they're not very efficient. So so there are not too many systems for which this is happening, and this is a summary of where you have L2 leakage in the parameter space of the mass ratio and of the mass of the companion. So it's only somewhere in this range. You don't want too much.
Is it obvious that the corona is insignificant because that will easily spill over?
Corona of what? Of the star? Yeah, so you lose it very quickly. So I guess if there would have been a corona in here, that's gone. So now you have to, if you're interested in corona, you have to see what time scale you build it again, and so on. I don't know.
I guess the thing that Chris is getting at is that the star will be rotating very rapidly, will it not, compared with what it would have been on the main sequence if it was at least it was a convective star.
My guess here it would be, I think it would be tidally locked.
Right.
Yes,
And that's going to be
that's fast.
yeah, it's very, very fast.
Yes.
And so it'll be very magnetically active, and so the mass loss, of a young magnetic active star might be much, much larger than the sun.
Sure, but but also the time scale at which the system evolves due to gravitational wave is also short. It's a million years or even less than that. Okay, so everything is relatively fast here. Okay. And this is just to show that this is detectable. This is the frequency in which we expect those events. So the frequency is something like 10 to the minus 4 hertz. So it's the LISA band. And it's easily detectable both in the Milky Way and in Andromeda, especially with the original plans for LISA, not the shrunk one. So we can see that in our galaxy and nearby galaxies, but not too far away. Okay, hypervelocity stars. I mentioned them already. This is again an artist description of one. So this is a binary that was in the galactic center, came too close to the black hole. The place at which it's happened is the same thing, but now here you put the mass of the two stars, the mass of the binary, but it's still two solar masses instead of one solar mass, doesn't matter so much. And the radius here becomes not the size of the star, but the separation between the two components of the binary. So when that happens, you have a disruption of the binary. What you can show, we can do similar calculations like this, is that the ejection velocity is the original velocity of the binary component relative to one another times the mass ratio to the 1/6. Okay? So 1/6 seems like this is not going to be important, but this is super important. Because if you think about it, the highest velocity that a binary can have, two stars can have relative to each other just because they're orbiting each other, is the escape velocity from the surface of the biggest of them, right? But the escape velocity from stars, main sequence stars, because the mass and the radius are roughly linear with one another, gm over r, which gives you the escape velocity, is constant. So the escape velocity for all main sequence stars is roughly the same. And that is a few hundred kilometers per second, okay? So if you see, and we see, stars flying away from our galaxy at velocity of 1,000 kilometers per second, that couldn't be that you just had a binary and one component of the binary dissolved, and therefore you see the other one, because those are still just a few hundred kilometers per second. And m over m, which is 4 million, to the 1/6 is about 10. So that gives you the extra factor of 10 that can explain the observations. This cannot be more than a few hundred kilometers per second. And with this, it's a few thousand kilometers per second, which can now explain the stars that we see, which have about 1,000 kilometers per second. And that is also 1,000 kilometers per second is also slightly higher than the escape velocity from the galaxy, which is also a few hundred kilometers per second. So those stars, not only they come up with high velocity, they also escape the galaxy. Okay, so this is the ejection. You can also talk about the radius of the bound star, the star that stays bound to the black hole. So as the binary comes, one star is ejected away with this velocity. You can take this velocity square that gives you the energy of the ejection, put that as a negative energy to the star that stayed bound. That will give you its energy and therefore its semi-major axis around the supermassive black hole. And you get that this is the original size of the binary times m over m to the 2/3. So there is a certain size there. Okay, I'll skip the details of that because I want to talk more about the dynamics of the stars in the galactic center. Tidal disruption events, it's very similar to that spillage of mass towards the black hole, except that it's not gentle. It's not a star that is just barely touching its tidal radius so that it spills mass very gently towards the supermassive black hole. It's a star that came on a very eccentric orbit. The eccentricity here, for most tidal disruption events, I will try to argue, is 1 minus 10 to the minus 6. Okay, so it's 0.999995969. Okay, it's very highly eccentric. And those are the majority of the tidal disruption events. They come in very close to the super black hole. They penetrate the tidal radius, which is here, and therefore they get destroyed in an explosion, not in a gentle way. Some of the debris, they gain energy compared to the zero energy orbit that the star had. Some lose energy. So the ones that lose energy have now tight orbits around the supermassive black hole, and they will return, these debris will return to the supermassive black hole within about a month, eventually accreting onto the supermassive black hole, creating some signals that we see. And people in this field debate on what is the mechanism exactly that caused these returning debris to come back and get accreted onto the supermassive black hole. What is the viscosity, and therefore what is the accretion rate, and therefore what is the signal that we should see? There are many interesting puzzles in here. One puzzle is that the observed rate of tidal disruption events, what we have seen in other galaxies, we of course haven't seen one in our galaxy, this is the expected rate. Once in 100,000 years in a galaxy. I will explain where this is coming from. So the observed rate is about a factor of 10 smaller than the expected rate. So we don't know what is the answer for that. Maybe, and you can always think of mechanisms that enhance the rate of tidal disruption events. It's hard to think of how to avoid this rate at least. This rate is just coming from two-body scatterings of stars within the galaxy. So we know there are many stars in the galactic center. They scatter each other. Some of them should come into the tidal radius, and this will happen to them. But maybe they don't produce the signals that we think we should see. So,
Or it's obscured.
or it's obscured, or we need a solution to that. There are many kinds of ideas. Obscuration, that the emission is different than what we think, and some other dynamical things that maybe I'll have time to mention. Okay, so here are the questions that I will try to answer with the dynamics that I will present. So first, what sets the slope of the stellar cusp in the inner parsec? Why do I choose a parsec? A parsec around the supermassive black hole in our galaxy is special, or 2 parsec. This is so-called the radius of influence of the black hole. This is where the mass of the black hole is equal to the mass of the stars around it. Okay? So I go at the very center, I have only the black hole. As I go a little bit outward, I have another 3 stars, 10 stars, 100 stars. And at this distance, I have 4 million stars, which is therefore the mass of the supermassive black hole. This is the radius of influence. And for our galaxy, this is about 2 parsecs. So how many stars are there within 2 parsecs? 4 million. Okay. If they're all one solar mass. If there are, most of them are less than that, and slightly more, and so on. Okay. What's that? Okay. Now, within that inner parsec or 2, how are they distributed? Are they mostly outside? Are they mostly inside? What is the density? Is it uniform? Is it a cusp? Is it, what is it? And we'll discuss that. And now, given a cusp like that, what is the rate that stars, because of scattering of each other, it's only because of scattering, right? Because at that tidal radius, the time to have one orbit is 100,000 years. Remember that 100,000 years from before. I said 100,000 years, 1 per 100,000 years is the rate of tidal disruption events. But now I'm telling you, 100,000 years is just the dynamical time to orbit at the 2 parsec, at the radius of influence distance. Just taking the 4.3 million solar masses of the supermassive black hole and the 2 parsec. That's all the numbers you need. You calculate it, 100,000 years. So if you had a star on a very eccentric orbit around the supermassive black hole, so eccentric that its periapse distance brings it within the tidal radius and it's going to be destroyed, this has already happened in the first 100,000 years. So if it's happening now, it's because it's a new star that got scattered into this new orbit. All the ones that originally had these orbits, they are irrelevant. They died. So every tidal disruption events that we see now is because recently someone scattered his friend into that deadly orbit, or his enemy. And one of the questions we want to ask is when they come into the tidal radius, how do they come? Do they come gently, or do they jump deep into the tidal radius? Some people think, I talked to U11, whose name I saw on the upper floor here on the plaque a few days ago, and he thinks that the reason we have this discrepancy between the number of observed tidal disruption events and real one is that the ones that come very gently into the tidal radius, they don't do much. They get destroyed in small pieces, and they don't do this flashy thing that we see as the tidal disruption events. And we only see the ones that penetrated deep into the tidal radius. So is that rare, or do you come and just scrape the tidal radius? It's important. And some people want to know the history before the tidal disruption. So when the star came every 100,000 years to have an orbit around the supermassive black hole, did it visit close enough that the black hole disturbed it? And then it came back again, and it's now a star that has a lot of history of visits to that supermassive black hole? Or is it someone that never saw this black hole before? And we want to know how many stars came to small orbits like that. They're also new stars, because the ones that used to do that, they don't last for more than 1 million years. So they died. We have to bring new stars into that. So these are extreme mass ratio in spirals, MRIs. We want to know what is the rate of MRIs. Which are more common events? How do stars die in the center of a galaxy? By tidal disruption events or as MREs? What is the ratio of those rates? Okay, so the problem that I think I know to solve is the following problem, which is not the real situation in the galactic center. So I'm maybe not telling the whole truth about the galactic center. So I take a black hole and I put it in a thermal bath of stars. This is more or less right. They have some velocity dispersion. In our galaxy, it's 200 kilometers per second. There is a radius of influence where you can think of the radius of influence in two ways. One is where the velocity dispersion of the galaxy is equal to the circular orbital velocity around the supermassive black hole, or where the masses of the stars and the black hole are equal. It's the same thing. This is it. Okay, so what are the simplifications that I'm doing which are not all correct for our galaxy? All the stars have the same mass. Okay, for simplicity, it's not correct, of course. I ignore something that is called resonant relaxation, which complicates the problem. There was a lot of discussion of that in the literature. I think at the end, it ends up not being too important, but it needs another investigation. I assume that the galaxy overall, at least the inner part of it, is spherical, and there may be deviations from that. And the most important thing that I'm missing, and I think that is not okay, and that has to be fixed if I want to get a realistic model of the galaxy, is collisions between stars. Stars have finite sizes, and when they go close enough to the black hole, you can calculate and show that collisions are more frequent than gravitational scattering, and I'm only doing gravitational scattering. So,
spherical symmetry is a significant simplification as well.
Yeah, I think this is worse. Spherical symmetry at the very inner parsec, I think it's fine. At the inner parsec, we don't see, there are some structures. Nothing is too huge there, I think.
Why do you ignore the billions of stars in the bulge?
The what?
So the bulge has 1 billion stars, but you only focus
Yes.
on million stars.
Yes.
Why is that?
Because they are the ones, I'll show you that the ones that are going to do tidal disruption events are the ones that are whose semi-major axis is about equal to the radius of influence. So stars that are far,
Is he so much higher?
yes, stars that are farther away, they may have tidal disruption events, but they are rare. And stars that are closer in, they also don't do too many. We'll discuss that in a second. Okay, so let me tell you about the history of this a little bit. There are two papers long ago trying to, in the 60s and 70s basically, trying to calculate the density of stars in such a situation. Exactly this problem with the same simplification that I discussed. The first one was by Peebles, and he decided that a steady state stellar cusp like that should have a density profile that goes like r to the minus 9/4. And shortly after, a year or two after, Bacall and Wolf, John Bacall and Wolf, I don't know which Wolf, but some Wolf, said that the density structure should be r to the minus 7/4, different than this one. And it's pretty complicated in their papers, but let me try to explain to you what is the difference, basically, in these two calculations. And then at the end, I will argue that Peebles may have the right answer in some cases. Okay? So you may have a little bit of that and a little bit of that in different regimes. So let me try to make some order in here. So one thing you can calculate is something called the relaxation time. How long does it take for stars to scatter each other significantly? So what does it mean significantly? It means that a star kicks another star with a velocity comparable to the orbital velocity around the supermassive black hole. So there is a cross-section to that. You take gm over v squared. This is the distance that the two stars have to pass from each other in order to change their velocity by v. So square that gives you a cross-section. Cross-section times velocity times density. This is the number of stars at distance r divided by r cubed. This is density. So density, cross-section, velocity gives you a rate. Inverse of that is the timescale, which is called the relaxation timescale. You can rearrange that. It's the period at that position times the mass ratio square times the number of stars at that distance. So let me just show you an interesting property of this relaxation time. If you walk this...
The number is possible,
No. The bigger the number is, you have more scattering, right? You follow a single star. If it has many friends, they will scatter in more quickly.
But you're holding M, little m fixed.
Little m is the mass of a single star.
Oh, and this is the total mass.
M is the mass of the supermassive black hole, because that dominates the total mass, because we're inside the radius of influence. I'm not doing the outside. Okay? Okay. But let's see what this comes up to be at the radius of influence. So let's see. At the radius of influence, there is the orbital time at the radius of influence. That's 100,000 years, I already told you. M over M is M over M, 4 million square. But what is this N? By definition, at the radius of influence, it's M over M, right? So basically, at the radius of influence, this and this cancel. So the relaxation time at the radius of influence is about 10 to the 5 years times another million, 10 to the 11 years. Slightly large, which means that the cusp of our central galaxy may not be completely relaxed. Maybe it didn't reach its steady state. Not all the stars scattered all the stars. But if I'm asking what is the rate of scattering, of strong scattering like that at the radius of influence, you see that there is one star scattered per orbital time at the radius of influence. Where do you see that? Okay, so we saw the relaxation time is this. It's bigger than the orbital time by 1 power of m over m. But within that time, I scatter all the stars. So how long does it take me to scatter one star? Just the orbital period. So this is why the rate in which we expect tidal disruption events is equal to the dynamical timescale at the size of the radius of influence.
That's not the same event.
It's not the same event, but we'll get to there soon, okay?
It's highly unlikely.
We'll get there, okay? But this is the time scale that you get a strong scattering. Yes, and I'll show you that it's the rate for tidal disruption event. Okay, so what basically Peebles' calculation comes to be, if you put it in the simplified way that I try to get that answer. Basically, Peebles says, okay, you have the radius of influence and half that and third of that, quarter of that, and so on. And you have scattering, which sends the star towards the center of the galaxy, towards the black hole. And if you're in a steady state, then the number of scattering at every sphere like that is the same. So we said, take the number of stars at some distance r, divided by the relaxation time at that distance, which we just calculated, and say this is constant. So that immediately gives you this profile. Just take n of r, divide by this, and say this is constant. That will give you the density. And this gives that density. What Bacall and Wolf said is the following interesting thing. As the scattering happens, there are some stars gaining energy, some stars losing energy. But as the energy close to the black hole is so much higher per unit mass than far away from the black hole, you remember the Schwarzschild radius of the black hole compared to the radius of influence is about 4 millions, the ratio between them. So it's huge. So for each scattering that sends some star to the center close, you have to throw away at the edge 4 million stars in order to take care of that energy. So basically what they said, the more constraining thing is not the particle flux, but the energy flux. Because as you try to shove particles in, the energy becomes a harder and harder barrier. So they said, they didn't say it this way, but the essence of what they said is, you have to take the number of scattering that you have per unit time, times the energy at that radius, and that has to be constant. And that leads to this profile. And now I told you that I will tell you that I think the answer is somewhere in between. So suppose, I'll say that now and I'll get to that in a second where it comes. Suppose this is radius. This is the radius of influence. This is the Schwarzschild radius. There is some big ratio between them, some several millions. And suppose that someone is creating new stars somewhere in the middle. Now that was not on the mind of those guys when they did that. They thought stars are coming from the radius of influence and flowing in. But in my story, some stars are coming here in the middle. So the ones that are trying to go inward from here, they fight an energy barrier because the energy is harder and harder inside. And they will have the Bacall-Wolf profile. But the ones that are trying to leak out, they don't have an energy barrier because the energy here is smaller and smaller. So their problem is actually particle flux. And therefore, I think they will have rho goes like r to the minus 9 quarters, and rho goes like r to the minus 7 quarters. So I think this should be the density profile. Now, what is that thing that is injecting stars somewhere in the middle? I will tell you in a second. Not in n-body simulations, but in some kind of simulations, which I will explain. Maybe I should say it now, because I'm jumping to the next subject here. So in my story, if there are enough binaries in the galactic center, when a binary comes to the black hole and it breaks, one companion is ejected as a hypervelocity star, and the other star has some characteristic semi-major axis. This is it. So if the main mechanism of bringing stars into the galactic center is the breaking of binary, there is a source of stars in somewhere about 1,000 AU away from the supermassive black hole. Those can now scatter each other inward or outward. If they scatter inward, they will follow the Bacall-Wolf profile. If they go outward, they will have the original Peebles profile that people thought is wrong. So I think we may have both in the galactic center if the source of stars to the galactic center is the breaking of binary, and that is right if there are enough binaries. If the fraction of binaries is similar to what we're used to from here, it is going to be important. Okay. Another process that changes the orbits of stars in the galactic center is gravitational waves. We discussed that in the beginning. If you know your GR, you can calculate the time for gravitational waves to operate. We can go through this. The way I remember this is if you have two equal masses, two equal mass black holes, they merge by gravitational waves in one orbit if they are touching each other. So basically two black holes of the same mass, they will merge in a timescale which is the Schwarzschild radius divided by c. This is the gravitational wave timescale. If they have some mass ratio, that's bad for the emission of gravitational waves. That makes it longer by 1 power of the mass ratio. So if you have a solar mass object around the supermassive black hole and it touches, let's say, a neutron star, because I don't want Roche overfilling and all the stuff we discussed. So a white dwarf or a neutron star, just touching the Schwarzschild radius of the supermassive black hole in the galactic center, it's going to make about 4 million orbits before it merges. So this is this. And then timescale grows in gravitational waves as the distance to the 4th power. So this was for two things that are touching each other Schwarzschild radius. If it's not, then it goes up to the 4th power. And if you have a very eccentric orbit, then it's even longer than that. So mostly the periapse, RP, determines the timescale, the shortest place where most of gravitational waves are emitted. But also the apoapse is important because if the star then goes and spends a lot of time in the apoapse, that increases that timescale. But there is some gravitational wave timescale. The two-body timescale for scattering, we have already calculated before. And now we can compare those two, and we can find where gravitational waves and two-body scatterings are equal. And it becomes a curve like that. And it's super cute because, let's see what is written here. Gravitational waves and two-body scattering are equal to each other. It depends on what the semi-major axis of the star is and what is its periapse. But if I look on stars whose periapse are at the radius of influence, this is the radius of influence, so this is 1, then the periapse has to be the Schwarzschild radius of the supermassive black hole. This is independent of the parameters of the problem. Super cute result. So we can display that in this 2D map, and then we'll come back to whether scattering is tidal disruption event same rate or not same rate. This will come from here. So what do we see here? This is possible orbits in the galactic center. This axis is semi-major axis. This axis is periapse distance. Periapse equals semi-major axis, meaning circular orbits. This is this line. Below this line, very eccentric orbits. Above this line, impossible. Okay, so nothing above this line. All orbits are within this triangle. Okay? The line we just calculated before, this one, at the radius of influence, it's equal to the Schwarzschild radius, and it has a slope of -1/2. So this is this line. So this is the radius of influence. This is the Schwarzschild radius. Okay? So the units here are the Schwarzschild radius of the supermassive black hole. So 1 is the Schwarzschild radius. 1 here is also the Schwarzschild radius. Here, it is just what happens to be the radius of influence compared to the Schwarzschild radius. Happens to be 4 million in our galaxies. There are 2 4 millions in our galaxy, weirdly enough. The ratio between the radius of influence to the Schwarzschild radius and the mass ratio between the supermassive black hole and the star, they're both 4 million. So this line starts in here and has a slope of -1/2. All the stars in here, they mostly have two-body scattering. This is what affects them. All the stars in here are mostly affected by gravitational waves. Now let's see what each of these processes does. If you have a roughly circular orbit and you scatter the stars, you can change the semi-major axis and the periapse roughly at the same rate. But if you already have a very eccentric orbit, let's say a point in here. What is a point in here? It's a star that is moving roughly at the radius of influence, but with a periapse orders of magnitude smaller than the radius of influence. 3, 4 orders of magnitude. So it's already a super eccentric orbit. Any scattering that you do to that star will change its periapse distance significantly, because you just twist it a little bit and it won't come back to the black hole anymore. But it won't change the semi-major axis by a small thing. So everything that is in here below that line of circular orbits, everything that is deep in here, only changes the periapse distance by two-body scattering. So that means going up and down in that curve. So when you're here, you can move anywhere you want. But once you fell a little bit below, you only go up and down. And therefore, the rate in which you scatter each other, basically, Yanchin, I'm answering your question, you can forget about moving in semi-major axis left and right, and all the dynamics is basically up and down diffusion in here. And therefore, the time scale in which you scatter stars in here eventually will all send them down to tidal disruption events.
It's not a 1D diffusion, right? Because Perry Center has angles.
Correct.
So it's 3D diffusion.
Correct. You'll do that, but still the rate, you have to supply them from somewhere. So the supply will be here. And what you're telling about, if it's 1D or 2D or 3D, it's actually 2D diffusion, will determine what is the density profile in here. But I don't care about the density profile. If I want to know the rate is constant along this, dictated by what is happening in here. That is my point. We can do that formally, but the gist of it is what I just said. Okay, so what I'm saying is, all the stars in here, they go up and down, and they may hit the tidal disruption radius. Now, the tidal disruption is about an order of magnitude bigger than the Schwarzschild radius in our galaxy. We discussed that in the beginning. So the stars that are doing that, they will have tidal disruption events. Even if they started here, they will go up and down, and they do tidal disruption events. But because I know the density slope of stars in here, I can tell how many come from here and how many come from here, and I can calculate that this is the dominant source of particles. So most events that are doing tidal disruption events, they're not doing that from deep inside the radius of influence, just barely at the outskirts of the radius of influence on super eccentric orbits with eccentricity of 0.99999 and getting destroyed. However, particles that are inner enough, they go up and down. They may want to become tidal disruption events, but before they do that, they hit this, what is that, light blue line. And then gravitational waves start to affect them. And gravitational waves, acting on a very eccentric orbit, they act mostly at periapse, therefore influence mostly the apoapse. So they take energy and angular momentum away from periapse, shortening the apoapse. In our diagram, that's a left-moving interaction. So they go up and down by two-body scattering until they reach that line, then they turn left, circularizing the orbits. And now once they have a circular orbit, they continue on a circular orbit until they hit that line, at which point they start giving mass to the supermassive black hole, which is the process we discussed in one of the first slides. So basically, I can tell you what is the rate between tidal disruption events and MRIs, because I know how many stars are here and will go up and down here and will do tidal disruption events. And I know how many stars are here according to this profile that will go up and down here, will hit that line before the tidal disruption events, and will turn. So therefore, here is my answer. The ratio between the rate of MRIs and the rate of tidal disruption events is the ratio between the Schwarzschild radius and the tidal radius squared. It's basically this. The bigger this is, the harder it is to get MRIs, because most of them will be by tides. Only those will make MRIs. The smaller this is, the more MRIs you have. So it depends on the mass of the galaxy, because if I take bigger galaxies, or basically bigger supermassive black holes in bigger galaxies, then the tidal disruption event radius becomes closer to the Schwarzschild radius. Eventually, you cannot have tidal disruption events anymore. The black hole swallows the star alive. So in galaxies which are of black holes which are 10 times more massive than the ones we have, this line will be right in here, and you'll have mostly MRIs rather than tidal disruption events. But in our galaxy, it's about 1%.
So -7.
Say that again?
Or -7.
Yes. Okay. Yes. So let's add to this story binaries. So before we add it up to here, and now we're adding binaries. Suppose some of these stars that we discussed before are actually binary stars. They don't care so much that they are binary. They scatter as a single star. So suppose there is a binary here. The binary goes up and down here by scattering. But before it reaches the tidal disruption radius of a single star, it will reach the tidal disruption radius of the binary, which is bigger because the binary is bigger. It's linear with the size of the object. It's what we have on the board there. So suppose at some time, let's say here, it got destroyed. Then we calculated before what is the semi-major axis of the surviving part component of the binary. One is ejected as a hypervelocity star. The other one stays in the center of the galaxy. And we had that on one of the equations before. It turns out that they all fall on this line. The surviving in this diagram, put in this way. So all dissolved binaries, the bound component of the dissolved binary is falling on this line. So if you have a binary here, it goes up and down by two-body scattering. And when it dissolves, one is ejected as a hypervelocity star, and the other one moves to this line. And from this line, it continues as with two-body scattering. But what you see here is that if the binary was tight enough, let's say the binary was almost a contact binary. So when would the binary be destroyed? Just slightly above where a single star would have been destroyed. So if you have a contact binary, it would go up and down in here. And just above this line, it gets destroyed. That means one is a hypervelocity star, and the other one falls in here. But here, that's below this line that says that gravitational wave equal the two-body timescale. So now, the surviving star will move only by gravitational waves and will become an MRI. So it increases significantly the rate of MRIs. It also changes the profile in the galaxy. It produces a lot of stars depending on the distribution, a lot of stars in the center coming from these destroyed binaries. And that depends strongly on the distribution of semi-major axis of binaries. So some people believe that many stars are binaries and many of them are contact binaries. In that case, many of them will come from here. They will move up and down. Somewhere here, they will get destroyed. The surviving component will go to that black line. and continue as an memory.
The pericenter of S2 is too high.
The pericenter of S2 is too high. So here, what you see here is the pericenter and apocenter of all these S stars in the galactic center. They're all above that. So basically, if they came from a broken binary, they came here, they broke, they came to that line, and now they evolved under two-body scattering. Most likely, they will go up because there's more phase space in here. Some of them may have gone down and done whatever they've done. So I think the situation is consistent. But we haven't seen, so basically the time scale to change the periapse here is short. So if you injected the star into here, you wouldn't find it after a while with the original periapse. So the original periapse will be lost. The semi-major axis will stay for a longer time. Wow, I'm way behind time. But I'm more or less done with what I wanted to say. So in this case, the ratio between the MRIs and the tidal disruption events is basically roughly the fraction of binaries that we have. Let me skip this last point about how do you populate the loss cone and where do these binaries get destroyed, and put it in my summary slide summarizing everything I told you. Thank you very much.
We're running a bit late, so maybe just one question and then we'll just conclude. So, last.
Yes. So add in collisions. What happened?
Okay. So collisions. I'll tell you what I know and what I don't know so well. So I can plot here where collisions are important. I can put lines in this figure. And collisions are important for a big part of this. Okay? Basically, people know it from the planetary case as well. Collisions are more important than scatterings at distances so close to the black hole or to the star in the planetary case, where the orbital velocity around the star is bigger than the escape velocity from the planet or from the star in this case. So you remember that the velocity dispersion in the galaxy, basically at the radius of influence, is about 200 kilometers per second. That is already comparable to the escape velocity from stars, which is just a few times larger than that. So when you go from the radius of influence just a little bit inward, the orbital velocity around the black hole is already comparable to the escape velocity. So most of this region is going to be dominated by collisions. The problem is, there are several problems now to create a full model. One is to understand what happens in a collision. When you have two solar mass or few solar mass stars collide, what happens? Do they shatter each other? Do they merge to a heavier star? And so on. People have done numerical simulations to this. All outcomes are possible. The other problem is that even if they merge and create a new star, their escape velocity is not higher. So they're still in the collisional region. So you have to think what will eventually happen to them. But collisions are important, and they take a big part in what is happening here. I think we need to do that to understand our galaxy, and most people ignore that.
Well, the distribution of observed S stars is an important strength in all of this. And you haven't yet explained to us where it really comes from.
This distribution of their eccentricity, of the distribution of what?
Observed.
Yes, okay, so you have to remember that these stars are the minority of stars. They are the most massive stars that we can observe.
They're special.
They're special. And they might also behave differently than the other ones because they are heavy.
Well, definitely the massive stars in the center aren't spread, they're distributed.
Right. So I don't know if that signifies something, and I don't know if there is enough of them to have statistics. There are more complete samples without resolved, well-determined orbits like these have about the density distribution, and it's not so easy to to make the comparison between the theory and the observations in this. It's not easy. It's doable.
Some peculiarities about the red giant distribution and stuff.
Right.
So actually there was a paper that came out just a few weeks ago that actually said that, so back in the day they said that there was positing in the number of red giants working like the center. But now they new observation that they found it. So it also tends to the same cast. So everything seems to work out.
Okay, I wasn't aware of that. And okay, good, interesting.
So just follow the, I don't remember, so if you look at they don't see individual stars, they see that just integrated surface density. So if you follow the one for mid-sequence stars, so the old plot showed that red giants followed up to a fraction of a parsec and then it leveled off. But now they said that I don't know what new thing they did, but now they claim to see the missing red giant, and it follows the same distribution of main sequence stars.
So for the main sequence stars, I told you it's a bit difficult, but what people are telling me, it's somewhere in between those two power laws. I didn't really see something too clear about this, but this is consistent with what we see. But I still have the question of what do collisions do. So of course, for red giants, the collision problem is even worse. You can have red giant collision. This is a bit rare, but huge cross-section. Red giant main sequence star collisions, some people claim they are unimportant. So the main sequence star will just go through and wouldn't affect the...
What it does actually, it separates the core from the envelope. If you see in the simulation, it sort of separates like yolk out of an egg.
Yeah, so the collision situation is not simple. It's complicated. You have to see what... Okay.
So let's thank them again and go up to